we are looking at acceleration, which of course you know is the rate of change in velocity per unit time. So here we have a race car that obviously is accelerating, though a bit in the wrong direction. And here is a space shuttle accelerating upward. The velocity is changing as time goes on. If we look at some motion diagrams here, this first guy really not moving at all, right? B, you can see, because again, each spot, each one of these guys is the same unit of time. Since those don't change, they don't get any further apart or closer together, we can tell this person is moving at a constant velocity. So if we have constant velocity, is there any acceleration? No, there is not. There would have to be some sort of changing velocity, which we can see in these two that are showing. Here he starts off close together and then further apart and further apart and further apart. We see that the motion diagram shows that, the particle model shows that, the dots as well as those nice vectors. All three of these are representing the same motion. On the left, this person is speeding up. He is moving faster if we're calling the right side the positive direction, the negative side the left direction, then he's speeding up, a positive acceleration. Whereas on the left here, on the right, this guy here, he is still moving in the positive direction, but his acceleration is in the negative direction. How do I know his acceleration is negative? Because he is getting closer together, right? Each of the time frames show him closer together. Negative acceleration doesn't mean you're slowing down. It just means the acceleration is going opposite of the positive direction. That's a key point to make sure that you are comfortable with. Okay? Again, velocity changes with acceleration. If it speeds up, the vector gets longer. As it slows down, the vector gets shorter. Somehow I lost a slide there. Let's move on and look at these vectors. By the way, that was on the bottom of page 69, moving over onto page 62 in your textbook. We have a series of vectors that are representing four motions along a straight line. Again, these are using both particle models and using vectors. So this guy up on top here, we have positive acceleration. Again, if we're saying positive is to the right and negative is to the left, we have a positive acceleration, starting out slowly and moving faster. For number 2 here, we have still positive velocity. We're still moving in the positive direction, but in this, so this would be negative acceleration. This would be a positive, well, let me put it in blue so it stays the same. This would be positive acceleration. But both of these have positive velocity. Why? Because they're moving in the positive direction. Number 3 here, the third one, this would have, we're starting off over here on this side. Here's our beginning. So we have negative velocity, and we also have negative acceleration. And you say, well, wait, Mr. Hess, doesn't negative acceleration mean you're slowing down? No, it just means you have acceleration in the negative direction. Versus our last one, number 4, this has positive acceleration. And how do I know that? Again, we're moving in the negative direction, but I'm slowing down. So therefore, the only way I can slow down if I'm moving in the negative direction is to have positive acceleration. So I want to make sure you're comfortable. Negative acceleration doesn't mean slowing down. Positive doesn't mean speeding up. It means it's just accelerating in the direction we've called positive or negative. Here are the velocity vectors don't know why we're not letting me work here, sorry. These are the velocity vectors. And when I add them together, I get this acceleration vector, right? If I took one of the vectors from up the previous and I add them together, I get these acceleration vectors that are showing you the direction that the acceleration is going, right? When the object's acceleration is in the same direction as its velocity, the velocity increases. If they're opposite, then the velocity decreases. That's the key point here. Okay, we can also use graphs. We're using all four ways of looking at this motion today. Remember, our particle models, our motion diagrams, our vectors, and our graphs. Here is a velocity time graph showing velocity on the y, time on the x. So this car, if we want to call it a car here, is speeding up, right? The velocity is getting larger as time is going on. So we can actually measure what is the acceleration, because we know acceleration is just the change in velocity over the change in time. This little delta guy here, that's just saying change in. Change is final minus initial, right? So the final velocity minus the initial velocity. In physics, we love to use these little deltas, these little change signs, which just means final minus initial. So if we pick two places on this lovely chart here, we're going to pick this one here and this one there, simply because they cross nice easy spots here. So we know that here at 4 seconds, we are going 8 meters per second. So that's going to be my final. And again, final always goes first. Final minus initial. So 8 meters per second. And then my second position is here, which is 2 seconds and 4 meters per second. So notice my 8 here, my 4 there, my 2 here, my 4 there. I divide 4, well, after I subtract them, I get 4 over 2. And of course, 4 divided by 2 is 2 meters per second. Notice there's not meters per second, it's meters per second squared, because I have meters per second divided by seconds. The units for acceleration are always meters per second squared. So in this graph, we are showing an object that has positive acceleration. We've created this being the positive direction, since these are both positive numbers that we're showing on the graph. So this object is not decelerating, it's not slowing down. If it decelerated, what do you think it would look like? It would look like the opposite, right? That my velocity is decreasing as time went on. What if we had constant acceleration? Well, then my graph would look like this, if I could draw a straight line. The velocity would not be changing over time. You'd have the same, in this case, a little over 6 meters per second, but it is not changing over time. Again, zero acceleration does not mean zero velocity. If we're doing a distance time graph, it's going to look like this. Notice it has this quadratic shape to it, the bit of a parabola. And that's because as time goes on, my velocity increases. Well, if my velocity increases, I'm going to cover more distance in the same time. So therefore, I start out very little bit of distance, and quickly as I accelerate, I get more and more and more. So you will always have a parabolic shape for my distance time graph. Distance time, not velocity time, distance time. And if ever there's acceleration, the velocity cannot be constant. All right, let's look at this graph that's on top of page 63. And it is showing you 5 different motions. I want you to pause this video, and I want you to actually, in your table groups, describe the motion of these five objects. Notice it is a velocity time graph. They have not, instead of giving you positive and direction, positive and negative, they give you east and west. They're calling east positive and west negative. So again, I want you to pause the video now and describe the motion of each of these letters, A, B, C, D, E. I'm assuming you're back now, and we are going to describe them together. Are you comfortable that A and E both show a constant velocity? How do I know that? The lines are unchanging. Their slope is 0. They are moving straight at the same velocity they start with throughout the whole entire time. Are you comfortable that both B and D show a constant acceleration? We know this because the velocity continues to increase, and it's a nice straight line for both B and D. So we know that those accelerations don't change. As a matter of fact, they have the same amount of acceleration because those two lines are parallel. But let's describe the motion. Whereas an A is simply going east at a certain velocity, and E is going west at a certain velocity, B does something different. It starts off at 0. It's not moving at all. And then the acceleration increases, and so its velocity increases on a nice steady pace, always going to the east, constant acceleration, the velocity is increasing in the positive direction. D, well, so let's go to C first before I go to D, because D is a fun one. C, actually, we are starting off with some velocity, moving in the east direction, because remember, this is velocity here, not displacement. So we're still moving east, but what's happening to C? It's slowing down. And I know that because this graph continues to go with a negative slope, so showing me this has negative acceleration, even though it's moving in a positive direction. Remember, we call it east positive. Even though it's moving in a positive direction, it's slowing down because of that negative acceleration. Then it gets to this point right here, and what happens to it? It stops. It stops moving. It does not continue in the west direction or turn back around and keep going east. No, it simply stops moving. Last but not least, the motion that has the most fun in it is D. D starts with a westward velocity, a negative velocity, and then it is slowing down. And you know that because it has a positive slope, an upward slope, so it has positive acceleration until it gets to a point where it stops. But unlike C, D keeps going. It then continues on in the eastward direction. So it actually is going west, slows to a stop, and then turns around and goes east, all moving with the same consistent and constant acceleration. If you look at the example problem that's there in, oops, sorry for the writings, the example problem number 2 that's there on page 66, you can see that we're looking at a ball that's rolling up a slanted driveway. And we want to know what is its acceleration. Well, we have its initial velocity is 2.50 meters per second, right? We know that it stops at the very top, right? So that's going to be the end of our motion. And we're trying to find out what was its acceleration. We also know that it's going for 5 seconds. So therefore, my VI is 2.50. My VF, my final, is 0.0. These are meters per second. And my time is 5.00 seconds. So we're going to use our equation, right? Our equation is that acceleration equals VF minus VI all over T. And the change of time, we're assuming it starts at 0. So I'm going to solve this thing by simply plugging in my numbers, right? That 2.50 divided by 5 equals 0.500 with my 3 significant digits, because that's what I start off with. But let me ask you, what direction is this acceleration going, right? If I am moving upward, I'm moving in a positive direction because we're moving up the hill, which we've said that upward is positive, right? And if I'm slowing down, therefore my acceleration must be negative. And again, my units are meters per second squared. So you're going to use this equation of acceleration is velocity final minus velocity initial divided by time to solve those problems. What I would like for you to do now is to go into your textbook and to complete numbers 1 through 10. You can work in groups together to solve it, but everybody needs your own paper to turn in. I'll see you when I get back.